Let's go ahead and practice two-column proofs of these predicate logic statements. So we start just by putting together all of our givens. Okay, this is always how you're going to start two-column proofs. And then we've gone ahead and asserted our desired conclusion. Okay, now since we've made an assertion, it has to be followed up with subnumbering and an assumption. Since we did not assert a conditional statement, direct proof is off the table, so we're going to do an indirect proof. We're going to assume exactly the negation of what we asserted. We asserted not P of B, so we assume P of B. Now let's look at our givens and ask which givens can we possibly use with this assumption. Lines 2 and line 3 don't have anything to do with P, but line 1 does. However, it has P of x and E of x. So notice that this involves P and E being true for the same variable. We have just assumed P of B, and we were given E of B. So we're going to go ahead and conjoin them, P of B and E of B. Now we have the statements capital P and capital E true for the same variable B. We were also given that for any variable, if P and E are both true, then we get S of XA. Therefore, we apply universal modus ponens. Okay, since P and E were both true for B, then we can conclude S of B, comma, and this A is just a free variable. But we were also given that we do not have S of B, comma, A. So if we conjoin those two, we have now generated a contradiction, which concludes the indirect proof of our original assertion, not P of B, which was what we were trying to work towards. Here's another one. Well, no surprise, we begin by stating our givens. Okay, let's think in advance. We're trying to prove there exists an x for which P of x and Q of x are true. We know that for any x, P of x is true, and there is something for which Q is true. So can there be something for which P and x are both true? Intuitively, this is sensible. Whatever the thing for which Q is true, it must also be true for P, so I can use that specific thing to be true for both P and Q. And as soon as I found something for which P and Q are true, there must be a thing for which P and Q are true. So that's what we do. We generate a specific thing. Specifically, we're just going to use A. We could have used any free variable we wanted here. But I need to instantiate both of these givens with the same variable, because I want to generalize it later where they have the same variable. So I need to be careful, and I need to do the existential instantiation before the universal one. But now I have Q of A and P of A both true for the same element. Therefore, I can conjoin. And now we existentially generalize. Okay, so let's just take a look line by line at what we did. We stated our givens, no big surprise. We were able to instantiate line 2 as Q of A. Okay, because A has not appeared as a free variable anywhere and wasn't in a given. Okay, we can then instantiate line 1 with P, and that's a universal instantiation, so it doesn't matter. Then we can conjoin P of A and Q of A and existentially generalize, which is a pretty unrestricted step. The thing we had to be careful about were these two lines. They can't appear in the opposite order. The existential instantiation has to come before anything else involving this variable A. So we had to do the existential instantiation before the universal one. Okay, here's another example. We've got a whole bunch of givens and one conclusion. It would be a little tricky to actually try to verbally discuss this. For any x and y, if you have A of xy and P of x, then you must have Q of y. For any x, G of x implies Q of x. M and N are specific variables for which A of M, comma M or G of N is true, and P of M or G of N is true. Therefore, there must be an x for which Q is true. Honestly, I can't just think about these intuitively and make a whole lot of sense out of it. We're going to have to rely on the form. So we state all of our givens. Okay, now our desired conclusion is there is an x for which Q of x is true. We could technically assert that, but that will actually be trickier to work with. What will be easier to do is to assert Q is a particular element, N is a particular element for which Q is true. Now, how did we know to use N? So let's look at all of our givens. Okay, we want Q to be true for something. there are two ways we're going to be able to extract that Q is true for something. Either G of something implies Q of something, or A of X comma a second thing and P of something implies Q of that second thing. So there are two reasonable choices given these two givens of what I might think Q can be generalized from. Either Q of n, because a G of n will imply Q of n, and I do have two givens that involve G of n, or perhaps Q of m, because A of X comma something will imply Q of that thing, and I have A of something comma m. So I could have also actually had a Q of m as a reasonable assertion, but we're going to go ahead and hope that Q of n works. Since we've made an assertion, we pass to a subnumber. It's not a conditional statement, so we're going to do an indirect proof. So, since for any x, g of x implies q of x, and we don't have q of n, we must not have g of n. That's universal modus tollens. We didn't specifically present universal modus tollens as a separate rule of inference that we proved, but it's basically the same as universal modus ponens, so hopefully this is not a terribly controversial thing to do here. Universal modus tollens works exactly like, modus tollens works exactly like universal modus ponens, just it's modus tollens, not modus ponens. Well, now that I have not g of n, we've got two things we can do with our givens in line 3 and 4. We can resolve both of them. And now, by resolving the given in line 3 with not g of n, we extract a of mn. With not g of n here, we get p of m. And we can join both of them so that with line 1, now I have a of mn and p of m. Notice that these are the same variable. They are both m. Therefore, I can apply universal modus ponens and get out q of n. What's just tricky to keep track of and throws students off is we don't care so much in the given in line 1 that the variables are x and y. What we care about is that this one and this one are the same. This one and this one are the same. So we had a of mn and p of m. Yes, those were the same. So the conclusion is q of whatever this was. So a of m something and p of m, since these two were the same, I can extract q of whatever this is, q of n. And now we have exactly the opposite of what we assumed. We started off by assuming not q of n, we derived q of n. We can join those, now we have a contradiction. So this assertion is now fully justified. Why did we assert q of n? So that we can generalize q of n to there is something for which q is true. And that was the conclusion we wanted. Now, there is a version of this proof you could complete where rather than asserting q of n, you assert q of m. Why would you assert q of m? Because a of mm and p of m, since these two are the same, you could apply universal ponens and get out q of m. So there is a version you could do where you asserted q of m, and then you would have to justify that somehow.